previous video, we talked about how to develop the system curve for a specific water supply system. The system curve is the upward curve in this slide. And if a specific pump is being operated in this system under specific operating conditions, we will be able to draw its pump head curve. The pump head curve is the downward curve in this slide. When the pump is able to add head to the system, the upward system curve and the downward pump head curve will meet at what we call the operating point. This is saying the energy or power this particular system requires to deliver water at a specific discharge is met by the energy or power this particular pump can provide to complete this job. In other words, the operating point also signifies the operating conditions of the pump in the system. The operating point can change if we change how the pump is operated, or if we change certain designs of the system. We will talk about the impact of different changes on the operating point in a separate video. For most of the water supply systems, we rarely change the system for moving the operating point. It is because rebuilding the system is way more expensive than changing the pump, and it is often unrealistic. Rather, we can easily change the pump operation conditions to achieve this goal. For example, we can easily adjust the pump's shaft speed. A higher shaft speed will lift up the pump head curve, resulting in moving the operating point to a different combo of flow rate and pump head. The pump's efficiency varies at different discharges. To minimize energy waste, the goal is to set operating point at or around the best efficiency point, BEP. As mentioned, this can be easily achieved by adjusting the pump's shaft speed. In this slide, the blue curve is the system curve, while the curve highlighted in green in the pump head curve. The intercept of the two curves lies at a discharge corresponding to the peak efficiency point. By looking at the operating point, which is the BEP in this example, we can read the graph and estimate the following operating parameters of the pump. First, the operating discharge is about 10.5 thousandths of GPM, that is 10,500 gallons per minute. Second, pump head is about 60 feet. Third, the efficiency is approximately 82%. Moreover, the pump's brake horsepower is about 200 horsepower. There is often another type of pump performance curve that is related to the risk of cavitation, called the pump's net positive suction head, NPSH. Because it is the pump's NPSH required to avoid the risk of cavitation, to avoid confusion with the pump's NPSH available at the pump's inlet, the former one is often denoted as NPSHR, where R indicates required. And the latter one is denoted as NPSH, where A indicates available. We will discuss NPSH in a separate video in the future. As you can see, using the operating point to find the pump's operating parameters through performance curves is a straightforward task. Notably, not all the pump performance curves look the same. Manufacturers often prefer to prepare one graph for several pumps of the same model, as they share the same geometric characteristics and mechanical designs. For this example, we have Taco's Model 3013 FI and CI series. The performance curves were derived from a testing on November 1 of the year 2010, by operating these pumps at 1,760 revolutions per minute. There are 5 different pump impeller sizes tested for this model series, with impeller diameters being 13 inches, 12.125 inches, 11.25 inches, 10.375 inches, and 9.5 inches. For a specific system with a system curve shown as the blue upward curve in the slide, if we use the 12-inch pump for the system, the head curve will be the head curve of this 12-inch pump, no others. Here, we highlight this head curve and read. With the blue system curve and the red head curve, we can find the operating point, indicated by the red dot in the graph. Again, we can read the pump's operating parameters once we have the operating point. First, we have the pump's discharge, about 450 gallons per minute. Second, we have the pump head, which is about 140 feet. Then we can also read the pump's efficiency in operation. But we are doing it a little different than before, because the pump's efficiency is expressed in contour lines this time. The pump's operating point is between the contour line of 72% and that of 74%. It is relatively closer to 72%. Therefore, 72.5% as the pump's efficiency would be a decent estimate. Similarly, we can also see the dashed lines being the contours of brake horsepower. The operating point is between the brake horsepower contours of 20 horsepower and 25 horsepower, and it is close to the central line but relatively closer to the contour line of 20 horsepower. Therefore, a reasonable estimate for the pump's brake horsepower bhp could be 22 horsepower. Notably, the bhp can also be calculated using the pump head to find water horsepower WHP, and then using the pump efficiency to find bhp from WHP. Pause a minute for this equation if it slips from your mind. Additionally, we can also read the NPSHR, the required NPSH to avoid the risk of cavitation. Because the NPSHR is a curve increasing with discharge, we start with the previously identified discharge of 450 GPM, and then find its corresponding NPSHR. In this example, NPSHR is about 10 feet. Now you know how to read pump performance curves no matter how different they are from one problem to another.